Hey guys, and welcome to this video. So today we will play around with pruning in PyTorch, and we will also try to implement a paper called the lottery ticket hypothesis, finding sparse trainable neural networks. As always, I'm not affiliated with the authors, and I apologize in advance for any potential misinterpretations of the paper and bugs in my code. Anyway, here you can see a GitHub repo which was created by one of the authors, and I would definitely encourage you to check it out. Personally, I did not really inspect it in detail, and instead I just decided to prepare a minimal implementation myself, which should illustrate the main ideas, but by no means it is an attempt to reproduce the paper's results. Anyway, I hope you enjoy the video. Let me explain in my own words and rather informally what the lottery ticket hypothesis is about. It states that if we take any feedforward neural network with randomly initialized weights, we can find a subnetwork inside of it with very nice properties. This subnetwork is called a winning ticket. And what are the properties? First of all, after training, the winning ticket will generalize better, or in other words, it is going to have a higher test accuracy. Second of all, training of the winning ticket requires fewer steps than training of the original network. And lastly, the winning ticket has way fewer parameters than the original network. The authors mentioned that it is often less than 10 to 20% of the original number of parameters. Here you can see the actual wording of the lottery ticket hypothesis that was taken from the paper. Feel free to stop the video and read it. Anyway, I would definitely like to point out a couple of things. You can see that the authors define a mask vector called M that has the same size as the number of parameters of the network. One can actually obtain any subnetwork by element-wise multiplication of an appropriate mask M and the parameter vector theta. Another important point is that to compute the test accuracy, one also needs to have a validation set. The idea is to find the iteration with the lowest validation loss and then to compute the test accuracy using the parameter vector corresponding to that given iteration. The hypothesis states that there exists a winning ticket, however, it does not necessarily give us a recipe how to find it. Luckily, the authors actually do propose a procedure that will help us find it. Quite surprisingly, it is based on vanilla pruning. Anyway, let's focus on the first row of this diagram. We start with the original randomly initialized network, and we train it for a fixed number of iterations. Once trained, it is very likely that all parameters of the network will have different values than before training. Anyway, we then take the trained network and prune it layer by layer. In our context, pruning will simply mean that we removed a fixed percentage of weights with the lowest absolute value, or in other words, the lowest L1 norm. In this diagram, we remove a single weight per layer, which would correspond to approximately 16%. Now comes the important part. We only keep track of the pruning mask and completely throw away the actual weights of the pruned network. And the reason is that we will actually go back to the weights of the original network and just copy them. However, we will keep the results of the pruning by applying the pruning mask. And yeah, that was one iteration of our algorithm. If we stop here, it would be called one-shot pruning. However, we can actually repeat the same procedure as many iterations as we want. And that would be called the iterative pruning. Anyway, eventually we end up with a network that has a lot of prune weights. However, the weights that we did not prune will be equal to their counterparts from the original network. Here you can see the exact description of the algorithm that I just took from the paper. Lastly, I want to talk about our setup and simplifications that we will make in this video. So first of all, we will be only using the multilayer perceptron. The paper also investigates convolutional neural networks, however, we are not going to do that. Our dataset is going to be the notorious MNIST, aka the hello world of computer vision. The authors also run some experiments on the CFAR10 dataset, however, we are not going to do that in this video. Anyway, we will actually have 60,000 training samples and 10,000 validation samples, and note that we are not going to work with any test set. And related to this, instead of using an early stopping criterion on the validation set and then computing test accuracy, as was done in the paper, I believe, our ultimate metric is going to be the maximum validation accuracy over all training iterations. I'm not sure how good or bad of an idea it is, however, I decided to go for this setup to make the code simpler. Another important point is that we are going to make our lives easier by using a pruning module that is already included in PyTorch. I believe this module did not exist at the time when the authors authors published this paper, and if I'm not mistaken, their code implements all the pruning logic from scratch. Lastly, a small disclaimer, a lot of the code in this video was just a result of me improvising, guessing, since I did not really have the time and energy to go look for the official logic. So please keep that in mind and feel free to let me know if you find any blatant mistakes. First of all, let me give you a very quick tutorial on how to do pruning in PyTorch. And I will only focus on the features that we will need for the lottery ticket. Alright, so we instantiated a simple linear layer and we would like to see what parameters it has. And as you probably know, it has this weight parameter and this bias parameter. And both of them are, let's say, dense tensors. Now let us see whether it has any buffers. Buffers are nothing else than tensors that are not supposed to be trained. So nothing was printed out, which means that there are no buffers. And lastly, let us also look at the forward prehooks. Forward prehooks are, let's say, callables that are going to be called just before you run forward pass on a given module. It's an empty dictionary. All right, so this is the status before pruning. And now let us actually try to do some pruning. So as you can see, Torch has an entire module with multiple different pruning methods. However, what we are going to use is the L1 unstructured pruning approach. L1 stands for the L1 norm, and it means nothing else that we will prune out those elements that have low absolute value. And the fact that it's unstructured just means that we are treating all the weights independently. Here you can see the docstring. However, most importantly, you can see that we need to provide the module we want to prune and the name of the parameter and also the amount, which in our case will be the percentage. So let us try to apply the pruning on the weight parameter. So we wanted to prune out 50% of the elements. However, what's important is that it modified our linear model in place and then it also returned it. And the question is, what exactly was this modification in place? And to answer it, we basically rerun some of the commands we ran before. Right away, you can see that the weight parameter disappeared and instead there is this new parameter called weight original. Let us check the buffers now. So it's not empty anymore, and you can see that there is this weight mask tensor. And as you would guess, it represents what elements were pruned, corresponding to the zeros, and what elements were left intact, corresponding to ones. And if we print them side by side, we can see that it's the elements with low absolute values that were kicked out. For example, this one. However, elements with large absolute value were kept. Alright, and now the question is, did the original attribute weight disappear? No, it's actually there, but it's not a part of buffers or of parameters, and let's say it's just a plain Python attribute. And as you can see, it actually represents the element-wise multiplication of the mask and the original tensor. This is another way how to view it. The weight original and the weight mask are just the leave nodes, whereas the weight is not a leave node anymore because it's a result of some operation of two leave nodes. Here I just computed the element-wise multiplication manually, and you can see that it's exactly equal to the weight. And let me also highlight one interesting property, and that is that the gradient of the pruned out elements is always going to be 0 no matter what loss function we use. So here I just created some like random loss function. We compute the gradients. And as you can see, the gradients are 0 for the pruned out elements. Another interesting thing worth mentioning is where exactly the update process takes place. As you can see, the forward prehooks dictionary is not empty anymore, and there seems to be a hook. And without going into details, this is exactly where the element-wise multiplication of the mask and the original weight is taking place. And this forward prehook is always going to be called just before our forward pass. And that way we guarantee that the linear weight tensor is always up to date. Lastly, we also want to investigate what happens if we prune the same module multiple times. And as you can see, there's only 3 elements left, which actually suggests that we apply the second pruning only to those elements that survive the first pruning. So this weight tensor has 12 elements, 3 times 4. After the first pruning of 50%, we were left with 6 elements. And now after the second round of pruning, we end up with 3 elements, which is 50% of the 6 survivors from the first pruning. And what's interesting is that after this second pruning, we have a hook which is of type pruning container, and it basically handles all this logic of running pruning multiple times. And yeah, this is just a summary of what's inside of the model after 2 rounds of pruning. And in the code that we're going to write, we will actually also apply the pruning to the bias. And yeah, I believe that's all we need to know. All right, so first of all, let us just prepare our data, which is nothing else than the notorious MNIST dataset. And our idea is to just take a torch vision MNIST dataset and make sure we flatten the images into 1D arrays. And the reason why we do this is to simplify things, since we are only going to be using the multilayer perceptron as our neural network. All right, so we provide the folder where the dataset is lying or where we want to download it to. And then we just specify whether we want to get the training set or the validation set. Just when it comes to the terminologies, I guess you could also call it the test set, but throughout this video, I'll call it the validation set. And that's basically the set where we're going to compute the accuracy. And internally, we will have the storage vision dataset. First of all, we prepare this custom transform that is going to take a pillow image and cast it to a tensor. And then we will just flatten this image that is just a grayscale 2D image into a 1D array, throwing away all the structural information. And here we instantiate the torch vision data set, providing all the necessary parameters. Here we define the size of our data set. All right, and if we query a specific sample in our data set, we then get the feature vector, which is just a flattened 1D array with 784 elements, because the original image has a resolution of 28 times 28. And we also get the ground truth label, a number between 0 and 9. And yeah, this is all we need. Now the goal is to write a couple of utility functions related to pruning. And as you saw in the small tutorial, actually Torch does a lot of heavy lifting for us, but still we'll try to write a couple of helper functions to make it even easier for our use case. First and foremost, we want to write a multilayer perceptron module, because that's going to be the only neural network that we're going to be experimenting with in this video. So we let the user choose the number of features, which for MNIST is going to be 784. Then one can also choose the hidden layer sizes, and finally also the number of targets. And again, for MNIST, this is going to be 10. Internally, we will have this module list instance, and it will hold all the linear layers. And this attribute is kind of important because we will use it throughout the code to easily iterate through all the linear layers in the multilayer perceptron. So here we prepare sizes of all layers, including the feature vector and also the target vector. And we iteratively define all the linear layers, and then we create this module-less instance. So the input to the forward pass is nothing else than a batch of input features. And what we return is a batch of predictions or logits. All right, so here we just iterate layer by layer, and we always send the tensor through that given layer. And we also apply the ReLU activation with an exception of the last layer. Cool, that's done. And now we would like to write a couple of pruning helper functions, and note that all of them will be modifying Torch modules in place. And also there will be this pattern where we implement something for a linear layer, and then we just generalize it to the multilayer perceptron by iterating through all the linear layers and applying the same procedure to each of the linear layers. First of all, let us define a pruning of a linear layer. We provide a linear layer to be pruned, and we also provide the percentage of elements to be pruned, both in the bias parameter and the weight parameter. Finally, we can choose a method of our pruning. We saw the L1 pruning already. However, we will also support random pruning, which we will use as a benchmark in the experiments. So based on the method string, we define the prune function that we want to use, and these functions are just outsourced from PyTorch. And exactly as we saw in the small tutorial, we actually apply this pruning to both the weight and the bias. And now we will just define what it means to prune an MLP. So not surprisingly, we provide an MLP instance. We also provide a prune ratio. However, we have two options. Either we provide the same prune ratio for all the linear layers inside of our MLP, or we can actually have a different prune ratio for each of them, which can be achieved by providing a list here. And the reason why we want to have different prune ratios for different layers is because in the paper, the authors mentioned that the pruning they applied to the last layer was smaller. And finally, we choose what pruning method to use, and this one is going to be the same for all layers. Here we do input validation. And we simply iterate through each linear layer, and we use the prune linear function that we defined above. Okay, now the goal is to write a function that will quickly check whether a linear module was pruned or not. For this check to evaluate to true, we want both the bias and the weight to be pruned. And the way we do this is that we look at all the parameters of the linear module, and we make sure that it's exactly the weight original and the bias original. And because that's basically a way how we can detect that a linear module was pruned or not. All right, the next function is going to reinitialize a linear module with random weights. And again, it is going to happen in place. The goal of this function is to work both on linear modules that were pruned, but also on linear modules that were not pruned. And we want to make sure that the pruning, or let's say the mask, is not going to be modified by this function. And by the way, the reason why we want to have this function is because we will investigate whether the winning tickets are only good because of the mask that was generated by pruning, or whether it's also because of the initialization of the original parameters. All right, so first of all, we establish whether the linear module was pruned or not. And then we just extract the actual learnable parameters, weight and bias. Here we reinitialize randomly both the weight parameter and the bias parameter. By the way, this logic is just coming from the constructor of the linear layer taken from the Torch source code. And now we will actually use this method to define what it means to reinitialize the entire multilayer perceptron. And yeah, the same logic here again. We just iterate through all the linear layers and apply the reinitialization linear to each of them. And now we want to define a function that is going to copy the weights of one linear module to another linear module. Also, we make an additional assumption that the first linear layer is unpruned, whereas the second one is pruned. And the reason why we need this function is because we will use it to create the winning tickets. Because as discussed, it's not enough to just have the pruning mask. We also need to reset the parameters to the original parameters. Here we run some sanity checks. And we copy both the weight tensor and the bias tensor from the unpruned linear to the pruned linear. And now again, we will just iteratively reapply this function to copy an entire multilayer perceptron. So the first parameter is an unpruned multilayer perceptron. whereas the second parameter is a pruned multilayer perceptron. And here we basically go layer by layer of both of the MLPs, assuming that they are identical when it comes to the architecture, and we copy the linear modules one by one. Finally, we just want to write an evaluation function that is going to compute how many prune parameters there are in each of the layers of our multilayer perceptron. And this way we can track it and have a nice overview once we run the experiments. So the way we count up the number of parameters per layer is just we count the number of elements in the weight tensor, and to actually get the number of prune parameters, we just count up how many times there is a 0 in the mask tensors. And we are done with all the utility functions. And now we can write a training script where we put everything together. What's going to be different this time compared to, let's say, my previous videos is that we're going to be using weights and biases to actually track our experiments. And the main reason for it is that we will have hundreds of different runs. And in my opinion, TensorBoard is not necessarily well suited for this given setup. All right, first of all, let us write a utility function that is going to loop through a data loader forever. It's actually a generator function, and the idea is that we will take an existing data loader and we will always, let's say, restart it whenever it stops its iteration, and we will just yield the same thing it is yielding. And actually, in our specific case, it's going to be a tuple of a batch of features and a batch of targets. Okay, now we would like to write a utility train function. And the reason why we want to put it in a utility function is because we will do training at two different places. First of all, we do the pruning, and the second use case is when we already have a prune network and we just want to train it from scratch and evaluate how good it is. So first of all, we will provide our neural network, and in our case, it's going to be the multilayer perceptron. Then we provide our training data loader. We also provide the loss instance that is callable and it computes the actual loss scalar. We also provide the optimizer. Here we provide the maximum iteration. This will control the exact number of steps we train the model for. That is why we actually implemented this infinite looping of the data loader. We don't want to stop when we do, let's say, exactly 2 or 3 epochs. We actually want to choose the number of iterations. Optionally, we can provide a validation data loader, and this will actually signal to us that we are not in this pruning phase where we try to determine the best weights to prune, and instead we are in this final training phase where we already have a prune model and we just want to train it from scratch. And finally, we can control how often we are going to evaluate and compute the validation accuracy. So we take our training data loader, we make sure it loops infinitely, and we also add progress bars. And here we iterate through our training data, and if the number of iteration is equal to the max iteration, we just stop the training. Anyway, we take the batch of features and we run the forward pass and we get the logits. We then compute the loss scalar, comparing the predictions with the ground truths. If we are in the evaluation mode, we will also track the actual loss with weights and biases. And this is the standard Torch boilerplate. We zero any previous gradients, we compute new gradients, and finally we take a step with our optimizer. And this branch handles the evaluation logic. So we basically iterate through all the samples in our validation set. We run the predictions and we compute the accuracy. And know that this validation accuracy is going to be the metric that we will use for evaluation of our experiments and making conclusions. And we just increment the iteration counter. All right, and that's it for the train helper function. Now I will just quickly implement a command line interface parsing logic. We've seen a lot of the parameters before, but I will just comment on those that are new. So the batch size is going to be 60. I think I saw this somewhere in the paper. This prune iteration will determine how many times we run the pruning. And if we set it to 1, it's going to be one-shot pruning. However, if it's going to be larger than 1, it's going to be iterative pruning. We initialize the weights and biases. And here we define a metric that is going to be the maximum of our validation accuracy. And I know that in the paper, the authors discuss early stopping and probably similar things, but here we make an assumption that this number is going to be the ultimate indicator whether our model is good or bad. Here we set the manual seed, and this will hopefully allow us to compare networks that were not pruned at all with, let's say, the winning tickets, assuming that all the parameters are identical. We instantiate the train and the validation data loaders. And here we define the hyperparameters of our multilayer perceptron. The number of features is 28 times 28 because we are dealing with flattened MNIST images. Then the hidden layer sizes. If I'm not mistaken, this is what they did in the paper. And finally, the number of targets is 10 because we have 10 digits. We instantiate 2 multilayer perceptrons, and the reason why is that the second one is actually going to be a copy of the first one. And what we're going to do next is that we are going to apply pruning to the MLP multilayer perceptron. And after the pruning, we always make sure we copy the weights from the original multilayer perceptron. Here we instantiate the cross entropy loss and also the atom optimizer. This learning rate was proposed in the paper, I believe. All right, and now we are ready to implement the first stage of what we're trying to achieve, and that is the train and prune loop that should result in a nicely pruned network. First of all, we take our overall pruning ratio that we want to achieve and we kind of distribute it to per round pruning ratios because there might be multiple iterations of this pruning and training loop. And here we implement the logic of applying the same per round ratio to all linear layers inside of our MLP, except for the last one. For the last one, we only apply half of that pruning ratio. I saw this in the paper. This variable defines how many iterations we're going to train our model for before we prune. I'm not sure if it makes sense. It's basically something I came up with. Maybe this first stage should be done in fewer steps. I don't know. All right, and here is our pruning loop. First of all, we train our network. And then we prune each layer inside of our multilayer perceptron. However, after the pruning, we make sure that we reset all the parameters to the original values. And now you can see why it was useful to create a copy of our original network. Finally, we also track some useful statistics. All right, so now we are done with the pruning phase and we have two options. We can either randomly reinitialize the parameters of our network and thus completely throw away the original weights, or we don't do any reinitialization and thus our network will have the original weights. And note that in both cases, the pruning mass is going to stay untouched. The main reason why we want to have this option in our code is to be able to run experiments that investigate how important the original weights are in finding winning tickets. The second stage is nothing else than to train our network one more time. However, now we want to monitor the training and the validation performance of this network very closely. All right, and we are done. I wrote a script that creates, let's say, a grid search over multiple different hyperparameters. And this is the place where the grid is defined. All of our experiments will run for 15,000 iterations. Then we want to compare the one-shot pruning versus iterative pruning, where the number of iterations is 5. We also want to compare L1 pruning versus random pruning. Here we have a bunch of different pruning ratios. 0 represents no pruning whatsoever. On the other side of the spectrum, we have 97% pruning, which is very radical. And here we want to investigate whether randomly initializing the weights after pruning has an effect. And finally, we have 5 different states. And the actual grid search looks like this. I'm using this tool Parallel, is able to launch multiple parallel processes. I believe that this grid generates more than 300 different experiments. And yeah, I already ran it on my computer for multiple hours. And now I'm going to show you the results. So I prepared a small report with the most interesting results. Let's start by double checking that the actual pruning was consistent with the desired pruning levels. First of all, let us look at those experiments where we only pruned in one shot. In other words, it is exactly those runs where the number of pruning iterations was 1, which is shown in the first column. The second column represents the actual pruning ratio that we computed after doing the pruning. And finally, the rightmost column is the desired prune ratio. As we see, there's basically a perfect correspondence between the actual and the desired prune ratio, which would suggest we did things correctly. By the way, it seems like there are only 7 lines. However, in reality, there are way more of them, but they are overlapping. Let me just point out that the 2 columns are not perfectly equal, and that is because of the last layer of our MLP, since we apply half of the desired pruning to it. And that is why the actual pruning is always a little bit lower than the desired one. Now let us look at the runs where the number of pruning iterations was 5. Each of these columns represent the actual pruning ratio after a specific iteration, and the rightmost column again represents the desired pruning ratio. And things look correct in this case too, since the actual pruning ratio keeps on increasing after each iteration. So specifically, if we, let's say, focus on one experiment where the desired pruning ratio was 80%, you can see that after the 0th iteration, 27% of the weights were pruned. After the first iteration, 47%, and so on, all the way up to 80%. Now let us move on to the main part of our results. As discussed before, the paper claims that to find the winning tickets, one needs to first of all prune based on the absolute values of the weights, which in this table would correspond to the L1 pruning method. And the second key to success is to make sure that after pruning, we copy the original weights rather than just reinitializing them. And the idea now is to actually look at our experiments and filter them based on these 2 criteria and see how they performed. And first of all, let us look at the case where we do random pruning and we don't reinitialize the weights. So what you see here is a parallel coordinate plot, and the first 2 columns show our filtering criterion. The third column is the prune ratio, and finally the last column is the maximum validation accuracy reached during the training. And as mentioned before, this metric is the way how we are going to measure the success of a given run. Right away, we can see that there is a clear negative relationship between the amount of pruning and the accuracy. And I guess the takeaway here is that if we care about accuracy, then we should not apply any pruning whatsoever because it degrades the performance. This negative correlation still holds even if we only focus on those runs where the pruning was not extreme. Anyway, this is definitely not the right recipe to find the winning tickets. Now, what if we apply the L1 pruning? However, once the pruning is done, we randomly reinitialize all the parameters of the network. Here, the results are very similar to the previous setup because it seems like the pruning ratio is negatively correlated to the validation accuracy. And unfortunately, it is always the case, even if we only focus on the runs where the pruning was between 0 and 80%. All right, then let us finally look at what happens if we apply the L1 pruning and at the same time we don't randomly reinitialize the weight of our network and we just work with the same parameters that the original network had. Here, the story is very much different. First of all, let me point out that I also show the prune iterations column to understand what effect it has on the final accuracy. And as you can see, it seems like the iterative pruning scheme leads to better results since there is a positive correlation. Anyway, what about the pruning ratio? We can see that if we include all the runs, the correlation is still negative. However, it is caused by the extreme pruning ratios above 90%. Let me discard them. Suddenly we see that there is a positive correlation, which is very impressive since it means that the more we prune, the better the accuracy is going to be, which is in line with what the lottery ticket hypothesis would suggest. Also, if we only consider those runs with iterative pruning, we can basically go all the way up to 93% pruning and still get basically the same accuracy as with the unpruned network, which is absolutely impressive. And finally, let's focus on the winning tickets a little bit more and let us fix a random state and inspect how the validation accuracy evolves over the training. Just for the record, I applied a little bit of smoothing to make the plot easier to interpret. So if we focus on the red line, it represents an experiment where no pruning was applied at all. And as you can see, it is consistently below the other lines with an exception of the black one, which represents an extreme pruning of 97%. When it comes to the best performers, they lie in the range of 50 to 90% pruning. And also let me point out that the pruned networks seem to hit the top accuracy way faster than the unpruned ones, which is again in line with the hypothesis. Okay, let us look at another random state, and the story is basically the same as with the previous one. The 97 pruning is a little bit too extreme. However, anything from 50 to 90% seems to outperform the unpruned network. Anyway, that's it for the video. I actually have to admit that I really enjoyed working on this one because I was able to get good results in the very first iteration of my experiments, which is not always the case when it comes to making these videos. Also, if I assume that there were no bugs in my code and that the experimental setup had no major flaws, I have to admit that I find the results to be very impressive, and they definitely give an interesting perspective on what is happening when we train neural networks. Anyway, if you enjoy content like this, feel free to like the video, leave a comment and subscribe. And I actually want to give a shout out to some of my viewers who suggested the topic of this video. And if you have any ideas for future topics, feel free to join our Discord server and I would be more than happy to work on them. Anyway, have a nice rest of the day.